Today we have lecture number 6. In this lecture, we will derive Reynolds transport theorem. Earlier, we have already done with the continuity equation and momentum equation, and we use a differential element approach. Today, we are going to start a fresh topic, which is Reynolds transport theorem, and in this topic also we will derive the continuity and momentum equations, but in a different manner, not using a differential approach but using an integral approach. So in today's lecture we will only derive the Reynolds transport theorem, and in the later lectures using the Reynolds transport theorem we will derive those governing equations in integral form. Okay, let's go through the content. First, we will talk about closed systems. We call it here control mass, and open system, we call it here control volume. We will look again into the two approaches we already have gone through, Lagrangian and Eulerian approaches, but we will look into the context of control volume. Then we will talk about extensive and intensive properties. You already know it from your first year thermodynamics course, but we will talk about here in a more generic manner. And then we will go into the derivation of Reynolds transport theorem. And in the end, we will interpret the net flux term of Reynolds transport theorem, which is present in the right hand side of the Reynolds transport theorem. Okay, let's talk about closed system. So once we talk about closed system, it means no mass can enter, no mass can leave. You know from the subject of thermodynamics, but here we call it the same closed system, we call it a control mass, because what is control mass is just a fixed collection of matter which is under study, and the amount of matter or the entity which is under study is not going to change as the time progresses. So in control mass approach, mass cannot cross the boundary of the closed system, so we are only talking about the same mass, same entity of mass all the time. Apart from the fact that the closed system is such that its boundaries can change its shape, it can deform, it can move. Just have an example of a piston cylinder arrangement. So we have a gas which is enclosed in the cylinder, and we are pushing the piston downwards. So what will happen is air is going to compress, and the dashed lines are representing the boundaries of the system. So here mass cannot enter because there is no opening for mass to go out. And so we call it a control mass. So mass remains the same, and no mass can cross the boundary of the system, and mass remains the same. So what we are doing is we are controlling the mass here. In contrast to if we look at an open system, so open system means mass can come in, mass can leave. So what we are actually focusing on or under study is a spatial region, volumetric region that is under study, and every time some mass is coming in, some mass is leaving this region of interest. So the boundary over which this mass can cross the system would be called as control surface, and just like the same as a boundary of control mass, control volume boundaries can change its shape, could be deforming, could be moving. We take an example here. Let's say we have a container where water is coming in from the top and leaving from the bottom. So the dashed lines representing a system which is under study, and as you know, there is something crossing the boundary. So some mass is coming in, as well as at this bottom some mass is leaving. So this could be called as a control volume, because it's an open system. Some mass can come in, some mass can leave, and the boundaries over which this mass is coming in or leaving would be called as control surface. So as we know that matter which is present inside the control volume, because every time new mass is coming in, some mass is leaving, so the matter which is present in this region of interest is changing as the time progresses. And because there is a mass coming in, there is a mass leaving, so every time you will find different particles here in this control volume. We already have talked about Lagrangian description. You can think of that observer is sitting over a fluid particle. So fluid particle, let's say a bunch of fluid particle is moving when time is 0. So at time t naught, the mass is this, and it has a particular shape, some arbitrary shape. But as the time progresses, the entity of mass remains the same. Its size and shape can change, but its mass remains the same. So we call that mass which remains the same. We are controlling the mass here. So this fixed package of mass, we call it a system. So system is thought of a material volume which the entity that is present in that material volume remains the same. So mass is no more changing. The bundle of mass can change its size and shape, but the entity of the mass remains the same as the time progresses. So we call here in today's lecture, we call this system or a material volume which is no more changing, which is being controlled. We call it a system. And we use a green letter to represent a system here in this lecture today. So that is our system. So every time the same mass is there, and you can think of, let's say, there is a die when the fluid is flowing. So you are just an observer. As the fluid is moving, the die is moving, but every time the entity of the die remains the same. So it means we are not, we are actually following the path of the fluid particle. So that is the essence of this Lagrangian approach. In contrast to Lagrangian approach, if we have a fixed region of interest, what we call it a control volume, and this fixed region of interest is something where some mass can come in, some mass can leave. So every time different entity of mass is present in that region of interest. So here we are focusing on a volumetric region, and every time new particle or new fluid particle coming in and leaving. So this approach is called Eulerian approach, because we have a fixed window and we are observing that every instant of time new fluid particles coming into that region. Some are coming in, some are leaving. So that would be called as a control volume. And here I have used a convention of representing control volume with a red color. So controlled mass is which is a system which is green in color, whereas open system where mass can come in and leave but region of interest is fixed is called a control volume. And I have used a convention here to red color convention for representing control volume. As far as our physical laws are concerned, so when you apply to a system which is a region of interest or which is a entity of some mass, our laws actually have been written as, for example, if we talk about Newton's second law of motion, so we talk about mass of the system, we talk about its acceleration is depending upon the resultant forces that is actually acting onto the system. So our laws are actually applicable to the systems not onto the control volume. So this Reynolds transport theorem actually provides us a framework in which we can convert the system into control volumes, because in control volumes something can come in, something can leave, and the laws are directly not applicable to the control volume, but conventionally the laws are applicable to the system. So Reynolds transport theorem actually provides us a framework where we can convert system into control volumes, and or vice versa. So this thing would be clear later in the lecture today as well. Okay, let's just check the understanding of system and control volume. So system is a fixed entity of mass, whereas control volume is a fixed region of interest where something is coming in and something is leaving. If I put a question, you have a deodorant, we call it a Reynold deodorant here. In case A, you can see that my system is defined by means of these dashed lines. The same is here in the scenario with scenario B, where you have a system and the system is representing. So once you define a system by means of the dashed lines, it means you are only focusing on the system. You are not bothered what is happening inside or what is happening outside the boundaries. We are only focusing on what is happening inside the boundaries. So can you answer this question? Which situation, the situation A or situation B is depicting the control volume approach? So just take a pause and try to answer this. What do you think about which approach, A or B, is control volume? Obviously, here you see in a system approach we are focusing on the same entity of mass, so our mass is not changing. We are only focusing on the same mass all the time, so that is my system. So it is the A is not a control volume, A is a system approach. Whereas in B, this B is a control volume, because in the region of interest there is an opening where mass can leave. So we are not controlling the mass because mass can go out from this opening. So that would be the approach B would be called as control volume approach. I mean this two approaches, control mass approach, which is a closed system approach, or a control volume approach, have some differences. For example, the basic idea is that in closed system we are only focusing on the fixed entity of matter, so the matter is no more changing. In control volume we are not talking about this mass, but we are talking about a space or a region or a volume. So something can come in into the volume, something can leave the volume. As you know, this control mass, it means if you are focusing on a particular bunch of mass, so all the time you are focusing on the same mass. So that would be called as a Lagrangian approach. Whereas in Eulerian approach, you are interested in the fixed region of space, and every time new particles coming in and leaving. So in closed system, obviously mass cannot cross the boundary, whereas in control volume, mass is allowed to cross the boundaries. Yeah. So in different branches of sciences, both systems have their applications. For example, in thermodynamics, we have learned first law of thermodynamics for closed system. We have learned thermodynamics for open system as well. So both have applications in different sciences because this Lagrangian approach is more mathematical, whereas an Eulerian approach is more practical approach, because you can only focus on a given region of interest and you observe that new particles is coming in. So this control volume approach is more practical, and in experiments we use this control volume approach. Because engineers are interested in studying systems, so as a broad we define system is something which is under consideration, the entities which are under consideration. Your system could be a closed system, your system should be an open system. This open system we call it a control volume. So if you see a control volume, obviously is a Eulerian approach, and this control volume could be either a fixed control volume where the region of interest is constant, is no more changing with the time, or it could be deformable control volume. It means as a passage of time the region of interest is either expanding or either contracting. So and if the system is a fixed mass of system, so we can think of the same matter or same entity. So that entity could be a small quantity of matter, we call it a particle approach, or we could have the collection of particles. Even these, if it's a particle, so as you know, in mechanics or kinematics, you are interested in a particular particle irrespective of its size and shape, and we see at a given instant particle is at some time somewhere, and after some time elapsed, the particle has moved to some other position, so it means it has displaced, so its rate of change of displacement would be its velocity, and its how fast its velocity changes would be its acceleration. So this is what your kinematics. So in rigid body, obviously you are not focusing on the deformation that has been taking place to the body. But in the subject of solid mechanics, you are not just interested in the rigid bodies. In mechanics, statics and dynamics, you are interested in rigid bodies, but in solid mechanics, you are interested in how the system deformation takes place within the body as well. Okay, so there are different approaches of studying, and this picture actually gives you the whole set of approach which is useful in understanding systems. When you talk about variables, you have seen that the properties are actually the entities that is actually representing systems. So for example, if we talk about mass, so if mass is 2 kilogram, you know is a small mass. If mass is 100 kilogram, you know the mass is much bigger. So extensive properties are such properties which are actually depends on to the amount of matter that is present in the system. So just like an example, mass is an extensive property because volume is an extensive property. Momentum, because momentum is a product of mass and velocity. So velocity is not extensive, but since it's multiplied with the mass, so more the mass, more will be the momentum. So it means the momentum is depending on to the mass of the system. That's why it is called as an extensive property. And if you look at energies like potential energy, which is mgh, so m, if you multiply by m, it means more the mass, more will be that energy content. So just like either kinetic energy, half mv squared, so more the mass, more would be the energy. And if it's a thermal energy like mcp delta T, where delta T is the temperature change, C is the specific heat capacity, then mass is a multiplier. So more the mass, more will be that energy. So all such properties are called as extensive properties. In contrast, such properties which doesn't depend on the quantity of matter that is present, just like density. I mean, if it's a half kg piece of gold or it is a 2 kg piece of gold, density remains the same. Or so density would be called as an intensive property which doesn't depend on the mass of the system. The same is true with the pressure and temperatures. Here in today's discussion, we will use letter D to represent the extensive quantities, and small b is a letter to represent intensive, corresponding intensive properties of arbitrary property B. So B could be any property which is an extensive. B could be a mass, B could be a volume, B could be momentum, B could be any property which is depending on to the mass of the system. The relationship between capital B and small b is obviously B is extensive property. If you divide by mass, M is a letter to represent mass, so you are going to get the intensive quantity. So for example, if I want to express energy like internal energy, kilojoules is an unit for energy which is an extensive quantity. So if I say kilojoules per kilogram, so then it becomes, we use a small letter to represent internal energy, U is a letter to represent internal energy, then internal energy becomes an intensive quantity. So this is the relationship between, or if you have an intensive quantity there, if you multiply it with the mass, you are going to get its corresponding extensive quantity. Mathematically, we can write it for a small differential element, let's say having a certain mass dm. So this is small region of particle, small region have a mass dm. So if you multiply with this extensive quantity, so mass is multiplied with b, you are going to get the corresponding extensive quantity. So I am going to get B multiplied by dm is an extensive quantity for a small region of interest. So if I add up all those small volumes into the whole control volume or integrated over the whole control volume, I am going to get the extensive quantity of that control volume. So it is very important to understand this expression, because this is B times dm is the extensive quantity of that small region of interest. So this differential volume, we call it a differential volume, and this differential volume, if you multiply B with their differential mass, you are going to get the differential extensive quantity. And if all these small masses bunch up together, then you will be able to get the total volume, total control volume of that extensive quantity. So here the expression for density is mass per unit volume. So mass would be density times volume. So this would be same thing as dm. So instead of dm, I can write rho b dv. dv would be nothing, just a small differential control volume. So this is a small volume. So if you have bunch of so many particles in this arbitrary region, if you add them together, integration means summing up together. If you sum up together, you are going to get that extensive quantity. So dV is a differential volume, which is the definition of density is mass per unit volume. So mass would be density times volume. So this is mass of this differential volume. So what I have done is I have integrated over the whole control volume. It means these small masses have sum up together to get the extensive quantity of this the whole control volume. So we can write in this manner. So this is an important expression, and what it says that you have a differential volume, and the extensive quantity, its corresponding intensive quantity is B. So rho times dV would be its mass, and mass multiplied by the small b, you are going to get its corresponding extensive quantity. Okay, let's move on to the approaches. So we have learned about control system and control mass. Let's say at a given instant of time, the system is represented by the green dashed lines, and the region of interest, which is the control volume. So at time t, what is happening? Both the system and the control volume are overlapping each other. So what we can say, what will happen after some time, some elapse of time delta t. Let's say delta t is some time after t naught. So what will happen? As you see, the region of interest remains the same, but since in this control volume some mass is coming in, some mass is leaving, so some of the mass has new mass has entered into this region, and some of the mass has left this region. So what will happen at time t naught plus delta t, that system has moved. Obviously, one system has moved, its size and shape has changed, but the region of interest, that is the control volume, which remains the same. So we can show it more clearly, the same thing. This region of interest, which is rad 1, that is a control volume, that region of interest remains the same. What has happened, this green is your system. So the system is something, it has changed its shape and size. So what we see here is the Roman letter of 1 is representing the mass that actually enters the control volume to fill the space when some of the mass has left the control volume. So 2 is actually the portion of that system that is no more a part of the control volume, and 1 is the region that actually has left the control volume, that actually has entered the control volume to fill the space when 2 has left. So it is very important to understand this diagram. So I am explaining it again. Let's say when your time is t naught, so at that time the entity of mass, which is system, which is in green in color, and the region of interest is the control volume, which is red in color, both are coinciding each other. So at that instant, the properties or the mass of the system and the mass of the control volume remains the same. What happens after small time delta t has elapsed? Then the region of interest, which is red, remains the same. Some mass come in, some mass has left. So actually the system, which is entity of mass, so in this region of interest, some mass, new mass has come in, and already what is mass present in this region has left. And we have clearly represent, because the red is a control volume which remains the same, and the green one is the system. So the system has some of the new mass has come in, we represent by a letter, Roman letter 1, and this is the Roman letter 2 is that system that is no more a part of the control volume because it has left the control volume. So in the next slide we will just represent this figure in the mathematical form, and if you understand this figure, then the derivation of Reynolds transport theorem would be very easy. Let's see this inventory balance. So at time t, this is the entity of mass you are interested in. So we use a green letter to represent a system. What happens to the control volume? Because at the control volume you have a fixed region of interest, and we are using a convention of red to represent the control volume. At time t instant, we have seen both system and both control volume are coinciding each other. So at a given instant, when no time has elapsed, then both are coinciding. So mathematically we can write it like this. We say that the extensive quantity of the system at time t is actually the same extensive quantity of the region of interest. We call it a control volume at that instance. So at time t, the extensive quantity of a system is the same as the extensive quantity of the region of interest. We call it a control volume. So B system at time t is same as B control volume at time t. So this is nothing, just a mathematical representation of the same fact that at time t the same mass is there in the given region of interest. So no mass has crossed, no mass has left. But as the time progresses, since it's a control volume, so some mass, new mass will come in, some older mass would leave. So we will see it mathematically how the equation would look like after delta t. So at time t, the thing is simple. This is the equation that is valid. What you call it, equation number 1. After some time delta t, what will happen? As you know, the region of interest remains the same, control volumes remains the same, but some of the new mass has entered into the control volume and some of the mass which was already present in the control volume has left. And that extensive property is represented by Roman letter 1 and 2 here. So this is my extensive quantity of the region of interest. And this would be the extensive quantity of the system. So mathematically we can write this equation. What will happen to my system? This is my system. So this system would be comprising of some of the part which is in the control volume. That is represented by this extensive property. That part plus some of the part that is actually present in the system is the part 2. But this system has there is no more the part of the system. So that's why I have minus of the Roman B1. So B2 is a part of system, P1 is no more a part of system. And some part of the B is which is common to the control volume as well as to the system, which I am representing this. So my system after delta t time has elapsed would be the extensive quantity of that system would be this part plus this part minus this part. So this is after delta t. What will happen mathematically we can write by this equation. So if you understand this, this is nothing, merely inventory equation, because some mass is coming in, some mass is leaving, the region of interest remains the same. So some mass is coming in, some mass is leaving. And the next is just manipulation of these two equations. So you understand the physics of equation number 1. What happens at time t? Control mass and control volume both are overlapping each other. So their extensive property remains the same. What will happen after delta t? Some of the mass has left the control volume, some new mass has entered and some mass has left. So if we are interested in what is the extensive quantity at time t plus delta t, would be this thing, which is some part of the system that is still a part of a control volume, we call it this thing, plus my system is comprising of the part Roman 2, this one, minus, because 1 is no more a part of system at time t plus delta t, so this part is subtracted. So you got equation number 2. Okay, so if you understand this, then the life would be easy. Equation 1 is just at time t both system and control volume are overlapping each other. At time t plus delta t, this system would be comprising of some of the overlapping part plus some part that is left the control volume minus the part that is actually entered into the control volume. So what I do is, now I do a mathematical operation of subtracting equation number 1 from equation number 2. So we are subtracting this equation 1 from equation 2. So minus is here, minus is here. So mathematically we have a minus here, we have a minus here. So we are subtracting. So what will happen? You got this equation, and then we just have to do the mathematical manipulation that we divide the delta t on both sides of the equation. So we have this, this quantity is the change of the extensive property of the system that has been taking place in time delta t. So what is the extensive property when time was t plus delta t minus the extensive property when time is t. So this is a change. Similarly, this is a change which is representing in this region of interest, which is the control volume. Yeah. And this is the mass which has left the control volume, this new mass which has entered into the control volume. If you break the right hand side of that equation into three terms, because this term, the term related to the part which has left the control volume, the part which has actually entered into the control volume. So at this point of time, you see that this equation is by taking the limit when delta t approaches 0, so this would be the definition of the derivatives. So that would be the material part of the derivative, because we are talking about system. So now you better understand this material derivative, because we are talking about the same material, and we are observing that extensive quantity has changed. What extensive quantity has changed in delta t interval, that is represented by the left hand side of this. And this left hand side is talking about the same entity of mass, that is the system. And right hand side is what is happening, what changes of that extensive quantities are taking place within the fixed region of interest. We call it a control volume. So this is something what changes takes place within the control volume. This part actually has left the control volume. So this is B dot out. Out part means that part has left the control volume, and this B1 part is that actually has come into the control volume. Some new mass has come in. So this is the B is any extensive property. So if you divide by time, B is, let's say, if B is energy, let's say, just think of B is energy per unit time. So it would be the rate of transfer of energy. So B could be any extensive quantity. It could be mass, it could be momentum, it could be energy, or it could be any extensive quantity. So the change in the extensive quantity of the system would be depending upon how much change taking place within the control volume, plus what mass coming out of this control volume, and what mass is coming into this control volume. So this is a very important equation. We call it an inventory balance equation. This is valid for any extensive property. And you see the left hand side is talking about system, the right hand side is talking about control volume, because in system no mass can change, but in control volume the extensive quantity change can take place because something is coming out, something is coming in. So that is actually the basis of Reynolds transport theorem, this inventory equation, and which is somewhat relating this system into control volume interconversion. So our laws are written in terms of system that can be represented for control volume, where some mass can come in, some mass can leave. Okay, the rest of the life is simple, because your inventory equation is having the left hand side is for system, the right hand side is for control volume, and we can see that B is an extensive quantity. So if you divide by 10, it would be the extensive quantity per unit of time. So it is exactly the same as extensive quantity. You multiply by the mass with its corresponding intensive quantity. Intensive quantities are extensive quantity divided by mass, and this would be the rate of change of mass per unit of time, and we use a dot to represent the rate. So B dot out means the rate at which the extensive quantity is leaving, and the B dot in would be the rate at which the extensive quantity is coming in. So this equation is very important, and what we can do is this left hand side is actually talking about the change that is taking place within the system, same entities. This is the change that takes place within the control volume. So this is the net, because something is going out, something is given. So this is actually the net flux of that extensive quantity which is taking place with this control volume. So right hand side is actually, if you look at it, is a control volume thing and it is a control mass thing, and this equation is representing the length between the control mass and control volume. Or if we look at very closely, this control mass is our Lagrangian part, and this is an Eulerian part, because it is talking about control volume. Something is coming in, something is leaving. So this is an Eulerian part, this is a Lagrangian part. And Reynolds theorem provides a framework in which it interrelates the control mass with control volume. So that's okay. We can write it for an arbitrary shape control volume, which is comprising of nothing, differential volumes. If you take the sum of all those differential volumes, you are going to get this control volume. And this control volume has a certain surface where something can leave or something can enter. That would be called as control surface. So this is a differential control surface. So if you integrated the whole differential elements across the whole arbitrary shape, if you take the sum of all those differential areas, you are going to get the control surface. We can write the extensive quantity of that system would be, we already have explained this, B times rho times dV would be dm, and dm multiplied by m would be an extensive quantity of that system. As we already learned from this first equation, that at a time t instant, the system coincides with the control volume. So same entity in a given region of interest. So we can write both are equal at the time t. So instead of B system, we can write B control volume. So this would be an expression for the extensive quantity of this control volume would be depending on this rho B times dV if integrated over the whole control volume. So this is the intensive quantity of this differential volume. If you take the sum, you are going to get the extensive quantity in this region of interest, what we call it a control volume. You see here this term is control volume, and the B out and B in can be represented by this integral. So at this point, you just think of what is coming in and out is always taking place from the surface, and differential surface is dA, and you know the surface is always represented by its normal. So the normal here is a unit vector that is actually representing the perpendicular direction of a surface. So if some mass is leaving, so actually it will leave in the direction normal to that surface, because it's an arbitrary shape. Everywhere the normal is in different direction. Here the normal is in different direction, here the normal is in different direction, here the normal is in different direction. So if B is a velocity vector, so there is some component of velocity that would be in the normal direction would actually leave, because if you resolve this velocity vector in terms of its two components, let's say one of the component would be parallel to the surface and one of the component would be in the normal direction. So the velocity part which is in the normal direction is actually coming out. The velocity component which is in the parallel to the perpendicular to this normal direction or parallel to the surface would remain into that region, which is not coming out of that region. So actually mathematically this B out and B in term is represented by this integral, and we will see the physical meaning later. Just plug into our inventory equation. This is our inventory equation, which is nothing. This is the rate of change of extensive quantity of the system would be depending on the rate of change of the extensive quantity within the control volume plus something extensive quantity coming out of the control volume, something is coming in. So B out and B in can be represented by this integral. Since out and in is through an area, we call it, this is an area integral. This is a volume integral. So this volume integral means the whole control volume. So if you write in calculus, it would be a triple integral. If you write in area integral, it would be a double integral, because we are integrated over the whole area, and once it is on whole area, then it will be a control surface. Mathematically, we can write this by bringing the right hand side because the rate of change of this BCV equal to this thing, plus B out minus B in is actually represented by this area integral. So the rate of change of extensive quantity within the system would be representing what change takes place within the volume. Here we call it an accumulation of that extensive quantity that has been taking place in this region of interest. And the whole mass that is present, the whole entity, would be depending on what is the extensive quantity that is present in this region plus the net flux of that quantity. So net flux of B, which always takes place because what is coming in and out is always taking place from the surface. That's why you have a surface integral and you have a control surface here. So this integral is a double integral. This integral is a control volume. It's a triple integral. And keep in mind here dV is a differential volume and V is a velocity vector and N is the normal to the surface. For every surface, to every surface the normal would be different. So what we are actually doing is at this moment of time we have taken our control volume fixed and the velocity is measured relative to the fixed control volume. In the later stage we will see this control volume could be a moving part as well. So this would then the velocity would be a relative velocity. Right now this velocity is relative to the fixed control volume, and this expression which is nothing, just substituting this equation and this equation in inventory equation, you end up with that equation. That equation is known as Reynolds transport theorem. So it's a very important theorem because it's relate the left hand side is a system control mass, the right hand side is a control volume, and control volume is means it's an Eulerian part, and this control mass is a Lagrangian part because you are only focusing on a given entity of mass or of fixed mass. Here it's an open mass, something change takes place in the region depending on what is the net flux of that quantity. So this is very important theorem and we will use it to derive continuity equation, momentum equation later using this Reynolds transport theorem. So it is actually an integral representation of the inventory equation we have already learned for a differential element in previous lectures. There is a net flux term, and I mean you can understand this B out and B in little bit further. If we look at something like velocity vector and normal, if it is in the same direction, you know the definition of a dot product of two vectors. V dot n would be magnitude of V, magnitude of n, and the angle between V and n. So when they are in the same direction, then the angle would be 0 and cos of 0 would be 1. And the magnitude of a normal vector is 1, so you end up with the magnitude of the velocity vector. So V dot n, which is coming out, the component of the velocity that is in the direction of the normal vector is the part of the intensive quantity B for a differential element coming out of the differential surface would be represented by this normal vector, which is V dot n out. Similarly, if let's say, okay, I have, actually it should be opposite, so I have made a mistake here. So if it's something coming in, this arrow is not in this direction, but arrow is in this direction. So it means the angle between the velocity vector and the normal vector is 180 degree. So this is incorrect here, I mean this arrow should be here. So it means the angle between the velocity vector and the normal vector is 180 degree. So it would be the component not coming out, but it would be the component that is going into through the control surface, it is going into the control volume. So because arrow is here for the velocity vector. Normal is always outward, normal is always perpendicular to the surface, but the velocity vector is normal to is in the opposite direction. So this is something, the flux which is coming in, this is the flux which is coming out, and we can represent both in and out by a simple V dot n. So this V dot n is actually representing what is going out minus what is going in. So out is something positive and in is something negative because it is in. So this is out is positive, in is negative. So the whole thing v dot n, if it is not in the direction or making certain angle, so we call v dot n, which would be v cos theta. So that either represent out or n both together can be represented by this integral. So the net flux is represented by this integral. So you better understand now all the terms related to this Reynolds transport theorem. You understand this term in physical meaning of this term, you understand this physical meaning of this term, you understand the physical meaning of this net flux term, because flux is always takes place from the area, because what is in the control volume coming out and coming in is through the control surface, and what changes takes place within the control volume is this, and the whole thing relates with the system. So this is how we finish our this lecture today.